Hi, and welcome to Practical Magic with Animations in Compose. My name is Rebecca, and I'm a Developer Relations Engineer at Google. Have you ever been given a motion design and taken one look at it and thought, there's no way I'll be able to implement this? Or you look at aspirational things on Dribbble and think, wow, I have no idea where to start. I'll tell you a secret. I was this person too, and I sometimes still am this person. But in my journey to learning how to create fun animations, like the ones you're seeing on screen now, I've come to realize that there are some practical steps to take when trying to implement a complex animation. In this presentation, we're going to be looking at this animation that a designer has given us. It's a non-standard navigation draw. We'll use the implementation process of this navigation draw to understand how to think about animations in general. So let's dive into how we can analyze and implement a motion design. After implementing many motion designs, I realized that there are some questions that I end up asking myself for each animation, which helps me either pick a specific API or figure out the complex details of an animation. Let's take a look at some key principles of animation. The three questions that I ask myself for each animation is the following. What property am I animating? When does this property animate? Is it on click or is it forever? And how should this property animate? Should it have a bit of bounce, or should it be a static animation over a set period of time? When we think of these three things, it gets a lot easier to break down our animation. So looking at these questions, let's think about the navigation draw that we are implementing and figure out how to answer the questions. Firstly, let's talk about what. Most animations are made up of changing different properties or values of a composable on screen. Usually, these are properties such as scale, translation, rotation, alpha, or color. The best way to approach an animation is to break it down and try identify individual properties of a composable that are changing over time. Sometimes breaking down an animation is easy because your designer has given you access to the tooling that they've used to make the design. This is the best case scenario. At this point, there aren't many questions to answer. You just need to figure out how to translate from the tooling into your code. But if you don't have this luxury, you might need to analyze a design or video and break it down yourself. So in this example, you might notice that we have two different states, and this is helpful for analyzing our animation. By looking at the different settled states that the animation will take and trying to fill in the blanks between them. The open state of the animation shows that the graph content is drawn over our navigation items, and the top content is smaller in the open state, as well as the corners of the sheet are rounded. In the closed state, there's no visible sign of the navigation draw at all. So we can identify that there are at least three properties in this transition that are changing. The translation X, the scale in both the X and Y directions, as well as the shape corners are getting rounded as it moves into the open state. So we have our app defined with an outer box and two custom composables. Home screen draw, which is the bottom layer that contains the draw contents, and screen contents, which will change based on which draw item is chosen. We also have our draw state stored in a mutable state. So with this code, we already have our starting closed state in the correct position. When it's closed, the screen contents draw over the navigation items. To apply transition between the two states, we can use Modifier.graphicsLayer. This is a great modifier to use for animations. It allows us to adjust properties such as scale X, scale Y, etc. The other great part about this modifier is that it runs in the draw phase of Compose. So any animation changes here won't trigger a recomposition, as it doesn't need to go through all the phases. In this example, the open state, we set the translation X to the draw width, and the scale X and scale Y to 0.8 to make it a little bit smaller, and the shape of the layer to be a rounded corner shape, which gives us the correct open state. Now this won't automatically animate between these two states. We've just defined the start and end state for each property. We can see how this looks. We have the start and end state of the properties, but it's not animating between these two states. Great. So we know the properties of our animation that we're going to work with, and we know that we are going to be using Modifier.graphicsLayer. And this is a great way to apply these transformations to our composables. Let's talk about when the animation should occur and triggering these animations. There are a couple of use cases for when an animation is normally triggered. For example, an animation can be triggered on a state change, on launch of a composable, infinitely, or with a gesture. Let's talk about each of these different options. On a state change, what does that mean? A state change can either be driven from a view model or an action that a user takes. For instance, the click of a button or the toggle of a switch, for example. Typically, for these kinds of state animations, we can use the AnimateAsState APIs. There are a bunch of built-in options, such as animateColorAsState, etc. These store and manage the value change over time for you. They are typically used for one-shot state changes. Let's look at an example. In this example, we have a Boolean clicked. We will adjust this value to true or false. Then, using the animateIntOffsetAsState value, we will change the offset based on if the item is clicked or not. Giving the new value of an offset, that should occur on click. The animateIntOffsetAsState function will automatically update on each frame, interpolating between the current state and the target value. We can then use the offset modifier to adjust the offset of the item that's visible on screen. This would result in the following as part of that state change. The other option for state changes is to use a transition object. This concept allows for coordinated state updates that'll happen at the same time based on state. The animations are not independent of each other, they happen at the same time. Let's take a look at an example of how transition works. In this example, we create a transition based on the current state. We then create two properties that will be animated at the same time. The first is the rect size, and the second is the rotation. These will be animated between the two values when the state changes. This would result in the two properties being animated at the same time. In this example, the scale and the rotation. The other option for running an animation is on launch of a composable, when it comes into view. This is typically when you start a screen. For example, if you had a placeholder that needs to be shown before the real content is displayed. To start an animation on launch of a composable, we can use animateAble. This animation object allows us to have control of our animation state, and we can then use launched_effect, which runs on the first composition or when the key value changes. In this example, we could use launched_effect side effect to call animateTo on our animateAble object. This will invoke our animation when the item is composed for the first time. Another option is to animate our content infinitely, or forever and ever. These kinds of animations can be created using Remember Infinite Transition. In this example, we create an animating scale that the text composable uses to scale content up and down for a pulsing animation. As you can see from this example, the hello text is repeatedly animating bigger and smaller. The other option for when an animation could be run is as part of a gesture. And this is how this particular design is implemented. A gesture drives how this animation is performed. When a user drags the sheet on top, it should perform the translation and scale. But this pattern can be applied to other components too. Gesture-based animations are interesting because they need to be interruptible when a touch begins, and they need to continue the animation after a gesture is finished, either decaying or snapping to a certain position. And it needs to feel like a natural stop. So let's get back to our example. Let's make the transition between the two states animate between with a gesture. Let's first start with the gesture, and then we can add the animation between the two steps. Firstly, let's look at how handling dragging of a composable works. To create a gesture between the two states, we can introduce an animateAble object. TranslationX. This will store the translation X that we can use to translate between the open and closed state of the drawer. We will update this value with a gesture. We can then use this value to set the translation X on the graphics layer, as well as use the same value as a fraction to calculate the scale. In this example, we lerp, or linearly interpolate, between 1 and 0.8, using the translation X divided by the draw width as the fraction between the two values. Lerp is a way to calculate where the fraction would lie between these two numbers, 1 and 0.8. So if we gave in a fraction of 0.5 between these two numbers, it would give us 0.9 as the answer. The next part we want to introduce is the draggable concept. We will use RememberDraggableState, and when the delta changes, we will make sure the animation snaps to the changed drag amount. We use snap-to because we don't want any animation delay when a user is interacting with the gesture on screen. The change to the translation X should be instant. Next step, we add the draggable modifier onto our screen content composable, and this adds drag gesture detecting onto our content. We say that we want the content to be dragged in a horizontal direction only for this interaction, and we pass the draggable state into the modifier. For a visual representation, we can see the start position of the x-axis is 0. When we drag on the screen, the drag amount is returned in the callback, and the overall translation x value is increased, which we then use with Modifier.graphicsLayer to move the composable horizontally. So running this now, we can see that the gesture is changing the translation of the contents on top of the other contents. This is looking good, except there are two issues. The first one is that the draw can be completely dragged off screen. And the second issue is that the draw dragging doesn't continue if I lift up my finger. We only drag when your finger is touching the screen. It doesn't continue if I perform a gesture and lift up my finger. So back to our code. To solve the first issue, we can either set bounds on the animatable object, or we could ignore drag amounts that get us above or below the threshold of what we want to allow. We will set a bound on the animatable object. This means that the animation cannot progress past these points. We will set it to start at 0 and end at the draw width. It's worth keeping in mind that this caps the animation at those 2 points. So if we wanted to overshoot the animation at some point, we shouldn't use this mechanism, and instead check the thresholds when we are translating with snap-to. Great, we've solved the first issue. But for the second issue, we need to think about what should happen when someone lifts their finger. Ideally, we want the animation to snap back into either one of the two states, open or closed. We need to take into account the current velocity of the current gesture, and use that to determine whether the animation should continue or bounce back to its origin. So let's talk about the case of handling flinging of the content. We've already dealt with the drag, but now we need to deal with the fling gesture. What should happen after the user lifts their finger is called a fling gesture. So back to our code. To do this, we need to calculate the current velocity of the gesture and use it to determine what to do when the drag ends. We first want to create a spline-based decay animation spec. This will be used to help us calculate the current velocity of a dragging gesture. How fast your finger moves on screen is the velocity of your gesture. Spline-based decay is just a fancy term for a natural-looking animation that will eventually come to rest at a certain position, given a current velocity. So to use this, we add the onDragStopped callback to the draggable modifier. This gives us the velocity with which the gesture finished, or the user lifted their finger. In here, we can now use the decay that we've created to calculate the decay value, given the current translation x values and the velocity of the gesture. This will give us an estimate of where the gesture would naturally stop, should it continue with the current velocity. The next bit that we need to determine is the actual target x that we want to head towards. We use the midpoint of the draw width as the decider, but this could be up to your implementation. In our case, if the potential landing point, i.e. the decay x, is greater than the midpoint, we want to target the open state, or the draw width. If it's not, then we want to target the closed state, or the 0 point. Let's go back to our diagram. So we understand that whilst a user keeps their finger on screen and drags, we update our animatable using snap-to. Now, when a user lifts their finger, say they perform a fling, we use the current velocity of the gesture to determine the estimated decay x value, or where it would naturally end up. If the point reaches past the midpoint, we know we are targeting the draw width as the final destination. In this case, the decay x ends up past the draw width, so we can naturally reach the destination using a decay. We call animateDecay in this case. If we can't naturally reach the target, say in this example you can see if we naturally decayed, we'd end up just past the middle of the screen. In this case, we want to just call animateTo with our current velocity, and this will take care of increasing the velocity and decreasing it to get to the target x that we want to get to. Okay, so back to our code. We can now introduce a Boolean called canReachTarget with decay that checks if the decay x is greater than the target x, and the target x is the draw width, or dkx is less than the target and the target is 0. So if we can reach the target with a dk, we call animateDK. Otherwise, we call animate2 with the velocity. And finally, we set the current draw state to the correct state that it is currently in after the animation. Additionally, we can also add a click function on click of the menu header that'll trigger an animation that opens or closes the menu. In this case, we don't dk because we don't have any current velocity in place. So as you can see, using animatable in this example allows us to control the value via a gesture or via a normal animation, making it a really powerful API to use. Right, so let's take a look at what it looks like now. Now we have a draw that snaps to the closest position based on the gesture and the velocity of the initial gesture. If we fling the draw, we can see it happens a lot faster than without it. Great, we've basically implemented the spec that we had in mind. But there's always a way to make this way simpler. From this example, we've essentially created what AnchoredDraggable was designed for. It's very similar to the draggable modifier, but it allows you to specify anchor points of the drag gesture. It's part of Foundation and was added in Compose 1.6.0 Alpha 3. In this example, our anchors would be the open and closed states of the draw. First, we defined our draggable anchors, open at the draw width and closed at 0. Next, we create the AnchoredDraggable state with an initial value of closed and passing in the anchors, setting the positional threshold to the midpoint of the drag. We can then change our modifier to use AnchoredDraggable instead of draggable, and use the state.requireOffset to get the translation x of the drag gesture. And this gives us a pretty similar interaction to what we manually defined in a more generic way. So we have our animation defined, and we are happy with it. But what if we wanted to customize it a little bit more? Maybe make it a little bit more exciting. The last question we need to answer is, how should our animation be performed? We should be thinking, how playful should our animations be? Or how long should an animation take in milliseconds? Once we've figured out how our animation should play, we could look into the APIs we have that can help us achieve this. Looking at an example using animatable, in this example, we are animating from 0 to 360 on launch of the screen. We have our animation set up and ready to go, but we want to customize how it runs, not just when or what it runs on. This brings us to talking about animation specs. Each animation is controlled by an animation spec, which stores information about the type of transformation. For example, if we are transitioning between 2 integers or 2 floats and the configuration. The following are animation specs that are available at the moment: tween, spring, snap, keyframes, and repeatable. The default that most Compose animations use is to use a spring animation spec. But let's talk a bit about tween specs. This spec allows you to specify how to animate between 2 values. Tween is just a shortened version of the word between, nothing fancy here. This spec is useful for when you want to set a duration in milliseconds for how long your animation should take. In this example, we've set it to take 300 milliseconds. So this is great to be able to customize, but what if we wanted to change how the value transforms between 0 and 300 milliseconds? Enter the concept of easing. Easing describes the rate of change of your animation over time. Easing is an interface that takes a fraction and produces another value. These easing functions are then used by tween to determine where a value should be in its execution. By default, tween spec transforms your values using fast out, slow in easing. A good example of how to think about easing and what makes a good easing function is like a roller coaster. A good roller coaster doesn't travel at the same speed throughout the whole ride. At portions of the ride, you're going faster, and hopefully at the end, you're coming to a stop. Similarly, with easing functions, using a linear function often isn't a great experience. It's jarring, and dare I say it, a little bit boring. Now let's learn a little bit more about linear easing. This is when you transform the values linearly. There's no acceleration or deceleration. In this example, when we change the easing curve to linear easing, the animation will run as follows. At 0 milliseconds, the x offset will be 0. At the midpoint, it'll be exactly halfway between the start and end values. And at the end of the animation, the X offset will be at its final destination. Another implementation of easing that looks a bit more natural than linear easing is cubic Bezier easing. Cubic Bezier easing allows you to follow a Bezier curve, where you can specify control point 1 and control point 2, the two control points that will determine the Bezier curve that the animation will follow. The example on the right has the easing curve defined by these 2 points that the animations will go between. A new addition to our APIs is the ability to create an easing curve from a path. We provide a path between 0 and 1, and in this example, we combine together two cubic curves to form a path that the animation will follow. We can then use these easing curves by specifying the easing parameter on a tween spec. This diagram shows the difference between applying different easing functions, linear easing and fast out, slow in easing, applied to the same animation. As you can see, there is a big difference between the two. Fast out, slow in seems more natural than using a linear easing function. So there are a bunch of built-in easing functions in Compose that should take care of most of your requirements. But if they don't, there are plenty of ways to define your own. Okay, so we've talked a lot about tween and setting the different easing specs to customize our tween animations. But at the start, I mentioned that by default, Compose uses spring animations for most of the built-in animations. Why is this? Well, spring animations are physics-based animations, based on a stiffness and a damping ratio. They generally look and behave in a more natural way than tween animations do. Let's look at how spring animations work and then understand why. Let's look at the problem with using tween compared to spring. Specifying a duration for an animation doesn't always work. For example, if we have two boxes, the first one only needs to travel a smaller distance than the other, but applying the same duration to both produces a very different look and feel for both. What if your device is larger? Say if you have a very large tablet, and you're animating from the top of the screen to the bottom of the screen. You'd see a massive difference in the animation between devices, as both of them need to complete the animation in a set amount of time, but with variable distances between them. The same can be said for interrupting an animation. For example, when I interrupt a tween animation and set a new target value, using tween doesn't work as fluidly as using spring, as spring animations take into account the current velocity, making it feel more natural. You can see from these two videos. In the first video, using the same duration for each of the same changes in position here just doesn't look as natural compared to the second video with a spring spec. Now if we look at what we can configure with spring, we can set two things, stiffness and damping ratio. This allows us to configure how bouncy an item will appear and how long an animation will take to come to rest. As you can see, using spring configurations allows us to create a whole different look and feel for an application. If we wanted something playful and fun, adding a little bit more bounciness to the animations can communicate this to users. Alternatively, if it's a bit more of a serious app, then removing the bounciness will ensure it communicates this more fluidly. Here is an example of using different spring configurations. Looking at each of these, you can see how applying a different spec configuration can communicate a completely different look and feel to your app, where the bouncy spec looks more playful than the others. Okay, so back to our example. What if we wanted an item to be a bit more playful and bouncy? We can change the animation spec used to be a spring animation and remove the decay animation to get a bit more of a playful effect on the app. We've covered some of the more basic APIs and principles of animations. And whilst most animations can be built up from simple primitives, luckily you don't always need to build from scratch for all kinds of animations. There are some predefined composables and modifiers that are built into Compose that take away a lot of the low-level work for you and complete it for you. The first one is animated visibility. It allows you to toggle the visibility of a composable with a pretty animation. For example, when used with a column, the items will automatically be removed with an animation. The next example is AnimatedContentSize. This example will animate size changes of content. Be sure to set the height and width after the AnimatedContentSize modifier for the changes to have an effect. The result of applying this to content can be seen as follows. A smoother transition between the two is now more apparent. AnimatedContent is another built-in composable that allows for easier animations between different composables. It allows you to customize the transition between different states and customize the Z order of the animation. For example, we typically can wrap when conditionals with animated content for more seamless transitions. So in this example, we wrap our content in AnimatedContent to provide a more seamless animation. Our transition between the different composables is now fading and scaling between each other, which looks a lot better than before. With animated content and a lot of the animation APIs too, there's this concept of an enter and an exit transition for content. We've recently introduced new options for this: scale into fit container, scale out to fit container, which animates the scale between the content based on the container size, as well as exit transition hold. This allows for holding the content in place till both transitions have finished. So back to the code. Changing the transition spec of animated content, we can customize how the new composable coming on screen will enter the screen, and how the old composable will exit the screen. In this example, we are using slide into container to slide the content towards an upwards direction, and slide out of the container in a downwards direction. We have also customized the animation spec to set a custom duration and easing function. Let's take another look at what this looks like. Our new content slides in from the bottom of the screen, and the old composable slides out from the bottom. Of course, this is customizable, so check out the different enter and exit transitions available to you in the docs. There are plenty of more built-in composables that you can use. If you're looking for a quick guide on getting started with animations in Compose, take a look at this link. Right, on to the last section of the talk. How do I pick the correct API for the job? When thinking about choosing an API for their job, there are many different options to pick from, and looking at the docs might have you overwhelmed. And whilst over time, you'll eventually get a feel for what API can help you, we do have many options to think about. Pretty much most animations can be built using a single animatable, or using the animateAsState function, as we've seen explained here already. But there are more handy options that you can use for your specific use case. We've recently released a new version of the decision tree diagram for Compose animations. It should help you getting started with thinking of which API would suit your use case. It's not meant to be strictly followed, as many APIs can be retrofitted for different purposes. But it should help you narrow your options and think of different questions to ask yourself about animations. For example, if we are thinking about animating the text color when an error occurs, let's follow the diagram to see where we would end up. First, we ask ourselves the question, is the animation like art? Is there a lot of SVGs or images being animated? In this case, no, because it's just text. Then, does it need to repeat forever? In this case, no, it doesn't, because it goes based on the state of if we are in an error state or not. Is this a layout animation? No, because it's the color of a composable, not the layout property. Next, we ask ourselves, do we need to animate multiple properties? In this case, no, it's just a single text color. Does the animation have a set of predefined target values? In this case, yes, so the animateAsState API is what we should use. And in this case, we have text, so we should also set text motion animated on the style property. The full diagram can be found at this link, and it should help you get started with thinking about which animation to use where. In summary, today we've covered a bunch of concepts for animations. But most importantly, try to analyze your animations with 3 questions in mind: what, when, and how. We've also learned that gesture-driven animations are typically made up of 2 parts: dragging on screen and flinging, and how to handle these situations. And finally, use the built-in components to make common animations easier. And if you don't know which animation API to use the decision tree diagram to help you decide. And that's it. Wait, what's that I hear? You wanted more? Let's do a quick bonus animation then. Let's talk a bit about image vectors and how to animate them. You might remember animated vector drawables. What if I told you if you don't need to create micro SVG animations in an XML file either? Let's take a look at this fun example of a jellyfish. Would you believe that this jellyfish is actually an SVG that we can break down and manipulate with code? Let's take a quick look at how we can do this. If we inspect what the SVG file for this jellyfish contains, we can see that there are a bunch of paths in this SVG for each bit of the image. We can take these path commands defined inside the SVG and build up the image in code in a similar way. For those unfamiliar, a path is just a set of mathematical commands instructing how to draw something. For example, Inside the path string, we can see these letters. They correspond to a certain command that performs something, such as a line to a certain point or a cubic curve. We want to render this vector programmatically with code. It's worth noting that we could use something like Lottie or load this up with AVDs. But for the sake of this example, we're going to be rendering this with an image vector. So to do this, first we take the individual paths defined in the SVG. We then create a vector using Remember Vector Painter and create an image composable, passing in the image vector that we are creating. We then add the paths to the image vector by creating groups that take in the path data and color. We repeat this process for each part of the vector of the SVG. And we now have a vector that is rendered in code instead of being loaded up from assets. This is useful because now we can animate parts of the image vector. So using what we've learned before, we can take the example and examine what properties are changing. We can see that the whole jellyfish moves up and down infinitely over time. So we should use translation Y and remember infinite transition. And the eyes blink when you tap on them. So we should animate the scale and alpha and use animateAble to have fine control over these touch events. Let's take a look at how to implement the blinking animation. We can create two animateAble objects, one that represents the alpha and one that represents the scale. We can then create a suspend function that we will call when the jellyfish is touched. We call launch, animating the alpha from 1 to 0, and then from 0 back to 1 after 150 milliseconds. The way we are calling animateTo here means that these two calls will run one after the other. The next part is that we can call launch again in this coroutine scope. This will ensure that the animation is run at the same time as the other launch block. And the scale is what we will animate here. We will animate from 1 to 0.3 and back again. Great, we've got our two variables. Now we can apply them to the actual vectors. First, we change the scale Y of the eye, so we can apply the animation value to the scale Y property of the eye group. Then, we apply the alpha animation value to the path full alpha. The same can be done for the translation Y, applying a variable that changes over time. And there we have a blinking jellyfish. And that's all. Building animations in Compose should be fun. For more information on the topics in this presentation, check out the links below. Bye for now.